Okay, so let's start continuing talking about value function approximation. So basically last time we talked about how we can do Bellman residual minimization in order to find the value function. So we talked about the population case. When the distributions are known, the only issue is that how to approximate these things. So I introduced some population level loss functions or also approaches to do it. So today I'm continuing doing that. But then if I have time, and hopefully I have, I'm going to talk about the RL case when we have only data, not the model, and the goal is to estimate like quantities like value function, Q function, or V. Okay, so here I just added one slide in the previous slide deck, which is basically saying that the Bellman operator the Bellman operator is a contraction with it's contraction with respect to the L2 norm that is defined with respect to the stationary distribution of policy pi. So what's the difference with what we had before? I mean, we talked about contraction of Bellman operator. What was the difference with those results that we talked in like the first few lectures? Any idea? Okay, so there is a comment in chat. Yes, exactly. So the answer is that we talked about supremum norm before, but now this is about L2 norm. But this is not about general L2 norm. It is an L2 norm that is weighted according to the station distribution of policy pi. So if instead of like this norm, if I had some other norm with respect to mu, and mu was different from stationary distribution of pi, then this would not be a gamma contraction necessarily. So it could be actually expansive. Okay, so that's the basic idea. Okay, so we talked about those slides and stopped here, which I want to now kind of talk about something called projected Bellman error. So here, just kind of as a reminder, when we wanted to do minimizing the Bellman residual, in the Bellman residual minimization, we were finding a value function that after applying the Bellman operator to it, we get this T pi V, which is possibly outside that function space. The distance between these two would be minimized. So that was the idea of Bellman residual minimization. So projected Bellman error, the idea is a bit different. So the idea is we want to find a point that after, say, we start from V, we project it to get T pi P, T pi V, and then we don't project it. We apply Bellman operator to get T pi V, and then we apply the projection operator to get back to this function space. So this is, I show it with capital pi with subscript f and mu. So this projection is essentially finding a point on that function space f that is closest to T pi V. So this is a kind of the closest, this distance, the closest distance from T pi V with some function on f. So the goal of this projected Bellman error is to minimize the distance between this V function and this projected point. So that's a basic idea. And we see that we have kind of a slight variation of how we formulate it. But this is the basic idea of projected Bellman error. And as we will see, many of the methods for solving this, finding good approximation of value function, when we have a function approximator, are based on minimizing this projected Bellman error. Okay, so as I mentioned, we find a V within function space f such that, for example, V is being equal exactly to projection of t pi v onto function space f. So that's one formulation. So we show it as a kind of equation or fixed point equation. Of course, if these two things are exactly the same, it means that the difference between them would be zero, right? The distance between them would be zero. We have this projection operator, which I'm going to define more formally soon, which is basically has two components. One is the capital F, which is the function space, and then mu is the distribution that we use for defining the distances. Okay, so this is the definition of projection operator. The projection operator is a linear operator that takes a function v in that function space, in any function that is defined in that domain. So that function is possibly and often is outside the function space f, and then it maps it to the closest points on f. And the question is that how do we define closest point? The closest point here is defined according to the L2 norm with respect to mu. So how is it? So we have basically projection of v onto f is a point v prime that belongs to function space f that minimizes this L2 norm, and L2 norm is weighted according to distribution mu. Is this clear? Okay. And I have just a note that if the distribution mu is clear from the context, we may just omit it and just write it as projection f, or even if f is familiar or clear from the context, just use capital pi as a notation. And this should not be confused with capital pi, which we used before as a space of policies or space of stationary policies. It should be clear from context. I try to make sure that I use a subscript f or f and mu to make it clear. But anyway, so some of the properties, it's good to think about them, or it's good to know. One is that, well, projection of some value function or any function belongs to the function space f. That's the whole point of projection. We take a point and we have this function space, we project it there. So the projection should belong to this function space. So it's kind of from the definition. The other thing is that if value function, it belongs to function space f, when we project it, it remains in the same function space. So essentially, if this is the function space and there's a point that is on it, I can't show it exactly, but this is on that, say, hyperplane. If it's a linear function space, after I project it, it just doesn't change its location, it stays the same. But if it is outside, it would change the location. Another property is the projection onto a subspace, kind of space that is defined by a set of basis functions, is non-expansive. So what does it mean? It means that if I take two functions, fv1 and fv2, apply the projection to them, the distance between those points would be smaller or equal to the original distance between them. So I guess this might be clear, like if we have, show a different color. Say if they're already on that space, so v1 and v2, after a projection, the position does not change, so it just remains the same. But if I have 2 points like this, if I projected, compute the distance here on F and compare it with the distance here in outside that F, the distance on F after projection would not be larger than this distance before projection. Okay, so there is a question. Does this require any assumption? Yes, so there are two, like here the assumption is just to be a subspace here. So if it is subspace, that's true. But also there is a more general function space. If the function space is closed and convex, then this is still true. But if it is not convex function space, then it may not be true. So what would be an example of it geometrically? Yeah, so maybe if the function space looks like this, maybe, and I have function, oops. So I have function v1 and v2, and this is function space f. So it's kind of, you see, it's not a convex shape. The closest point projection is here. So this would be pi of v1. This would be capital pi of v2. So you see the distance between them. Like originally it was like this, but then now after projection, it becomes like a larger distance. So if it is convex, it is not, if it is not convex, this does not hold. Here, I think we mostly talk about, or I guess always we talk about linear function spaces when we talk about projection. So projection looks like something that I have here. Okay. So the idea of projected Bellman error, or the idea was that find a V such that after projection, after applying the Bellman operator, getting out of that space and then projecting back, the distance between these 2 points be the same, like they would be the same point. We can also think about it as a loss function, making the distance between these 2 points the same. If it happens that they fall back to the same point, the distance, of course, would become 0. So we start from v is equal to pi t, capital Pi t pi v. We can define a loss function, and to define a loss function, we can think about some norm of the difference between these functions. So we say that we want this to be small. If it is 0, that's exactly the same. So to define smallness, we can define a norm on it. And there are different choices for norm, but a common choice is to use L2 mu norm. So we say that v minus capital P t pi v, according to L2 norm, rated according to distribution, some distribution mu. So that is called projected Bellman error, or mean square projected Bellman error. So PBE, projected Bellman error. And then if we define this, we try to find a value function that minimizes this projected Bellman error. This means that we want to solve an optimization problem that looks like this, that we find a V inside that value function space that minimizes this projected Bellman error. Or we can take sometimes squared of it. It doesn't change the optimization. Sometimes it might make the solving the optimization problem easier, or manipulation is easier. But that's the basic idea of projected Bellman error. Any question? Okay. So let's try to have a kind of a slightly different interpretation of it by just manipulating the objective function a little bit. So what we have is that, okay, so value function belongs to function space F. When we are optimizing it, we choose V to belong to F. This means that I can write V minus capital pi T pi V as pi capital pi V minus the same term. So I just wrote this is equal. This is because if V belongs to function space F, the projection of that point to that space would be itself. And the projection operator is a linear operator, so I just write it, like take the parentheses and write it capital pi, the projection operator, applied to V minus T pi V. Okay, so what was V minus T pi V? Right, remember, if it was 0, then it would be a Bellman equation, so the result would be that if it is 0, it would be V pi. But we also denote this quantity to be the Bellman residual of value function, or actually minus of that. So we say that V minus T pi V, it would be minus of Bellman residual. So what we are actually computing is we take the Bellman residual and then project it back to that space, which is, of course, clear. Like if we have this space, so this distance, so this distance would be the Bellman residual of V, or the difference between vector, not the distance. And now we project it to that space. So that this part would be the projection of Bellman residual onto F. And now we try to minimize its norm. So then the loss function can be written as V minus capital P, T pi V can be written as the projection of the Bellman residual of V according to some L2 norm. Okay, so is this clear? Perfect. Okay, so maybe this is a good time to compare the Bellman residual minimization and projected Bellman error. So Bellman residual minimization is minimizing this distance, as kind of indicated here. Projected Bellman error is minimizing this distance, or can be written as Bellman residual minimization, the distance between minimized V minus T pi V, the norm of it, LP norm of it, or which would be LP norm of Bellman residual. So here I wrote it as P, but just imagine P is equal to 2. So we are talking about the same norm. Here for projected Bellman error, I started talking about L2 norm here. So we are minimizing the projected, the norm of the projected Bellman residual. Here is L2 norm, but it could also be LP norm. So I could use this formulation to be more similar to this one. So that's a kind of the difference between these two. Okay, any question?
Are there any pros and cons in practice?
That's a good question. Well, we will see that later, that Bellman residual minimization, when you want to do it with data, you cannot really estimate it in an unbiased way. So in practice, if you just want to do Bellman residual minimization the way I defined it, you cannot really compute it. So there is that big issue with it. But projected Bellman error, you can. But then between these two things, like which one is better? If you could minimize them and if there was no bias issue. So you suppose you have the model and you can minimize it. And it's kind of, there's a lot of debate. Some people believe that projected Bellman error is more meaningful. So for example, Sutton and Bartu's book, they are strongly in favor of projected Bellman error. But there are other papers which basically show that it is not necessarily that one of them is better than the other one. And I think Sutton and Bartu's example is kind of like constructed to be that way, to Bellman residual not to be very well, but they're working very well. But there can be examples that projected Bellman error would not be small. But if I want to summarize, many of the methods that we use today are somehow based on starting from projected Bellman error instead of Bellman residual minimization. So in that sense, projected Bellman error seems to be more important or easier to work with.
Okay, thanks.
Okay. So there is another formulation of this projected Bellman error, which is, we can think of it as some coupled or nested optimization problem. So we formulate it instead of one optimization problem, formulate it as two optimization problems. So what are those optimization problems? One is assuming given T pi v, it computes a projection point. Remember, projection is the point that minimizes the distance, and the distance is defined by some norm. So projection itself, from a few slides ago, so here you see that projection operator itself is defined as an optimization problem. So one of the optimization problems that we are trying to solve then is going to be finding a point here that has the minimum distance to some T pi v. The other one is that finding a v that is closest to projection to this other point. So let me go through these optimizations. Okay, so maybe I start from the second one. So v tilde as a function of v prime is this v double prime minimizing over function space f that is closest to T pi of v prime. So this is as if I start from v prime here, I go to some T pi v prime, then I project it here, and that point would be v tilde of v prime. So just notice that this is a function of v prime. So if I change v prime, the solution v tilde would change. Now this first optimization problem is trying to find a v prime that v tilde of v prime, the solution of the other optimization problem, is close to v prime itself, which is essentially trying to find kind of, I show it here, v prime that, okay, so this was my v prime here first. So trying to find a v prime such that the distance between these two would be as small as possible. So this is another way of formulating it and makes the role of, or projection being an optimization more clear. And in some situations, if, for example, the function space is, say, not linear function space, and the projection is not having a very nice form, which I'm going to show later, then this formulation might be helpful. One other thing is that, okay, so this is formulation, this nested or coupled optimization. As I mentioned, if f is a linear function space, then projection has a closed form solution. So we can find the solution of this second optimization in closed form, and then we can plug it back to the first optimization and solve the first optimization. Also, if the function space f is general, it's not a linear function space, then finding the the projection operator, the effective projection operator as a value function is not going to be simple. So we may need to use numerical methods to solve it. The other comment that I want to mention is that this formulation has a regularized variance, which means that we add some regularization term to each of these optimization problems. And regularization, as you know in, say, your course in machine learning course, is useful to avoid overfitting. And that would be especially important if your function space is large. So there is a possibility of overfitting. So basically, if you have a lot of parameters, more parameters than the number of data points, or say, or if you're working with function space like reproducing kernel Hilbert spaces with a universal kernel, they can essentially fit any reasonable function, like continuous function. But you don't want to do that if you have only finite number of data points, so you want to kind of regularize. And this regularized variance have basically were developed in order to avoid that. And just as a disclaimer, I was involved in development of these methods. So that's why I'm also mentioning it. Okay, so let's go back solving projected Bellman error. But maybe before that, is there any questions so far? Okay, so let's think about how we can solve this projected Bellman error. And I'm going to talk about different approaches to solve it, and some of them may not appear to be related at all. But then we see that if we look at these different approaches, we see that many other methods in RL later are taking one of these approaches, and they develop algorithms based on those approaches. And the end results may not look very similar, but all of them can be seen as coming from trying to solve this projected Bellman error problem. So in order to, instead of talking about MDP and RL setting, let's talk about the problem of solving a linear system of equation for a few slides, and then we get back to this. Suppose we want to solve a linear system of equation, AX being equal to B or approximately equal, and A being capital, a matrix N by D matrix, X D-dimensional, B is also capital N, and N might be equal to D or large, greater than D. So if N is larger than D, then this is our determined system, so equality would not be satisfied. So let's see how we can solve it. Okay, if you want to, let's make it a little bit more interactive. If you want to solve it, what are the ways you can solve it? Just give some random thoughts.
Iterative methods?
Okay, yes, that's good. So can you explain a little bit more how iterative methods work?
Iteratively solve the linear equations being defined like the set, like Gaussian iterations.
Yeah, so I guess there are iterative methods, and I'm going to talk about them, so that's good. What else? You can take also inverse, right?
Yeah, I was going to say take the inverse.
Yeah. Kind of. I mean, we should be a bit worried if the matrix is not square matrix.
The pseudo inverse?
Or we can, yes, we can define pseudo inverse, yes. What else? Can you do gradient descent somehow, like using optimization techniques to solve it? Like, can we convert this to some function, like this solve a linear sum equation to something that is closer to the a typical optimization problem? So there is a comment. Okay, okay, so that's good. formulate problem as minimization of ax minus b. Almost, but ax minus b is a vector. So I think you need some small change. Maybe some size of ax minus b, the norm of ax minus b, and then minimize that. Okay, so these are all good. So I start from the optimization approach. So we formulate it as Brian mentioned, that we formulate an optimization problem where we have L2 norm of ax minus b and try to minimize that, or L2 norm squared, which would be, here everything is also finite vectors. So we write it as ax minus b transpose times ax minus b. Then to solve it as an optimization, we compute its gradients. The gradient of it would be A transpose times ax minus b. So this is kind of like ax minus b acts like the residual, how far we are from the solution. If it is 0, we are at the solution. And then this is kind of like changing to the basis of A. And then we can proceed using gradient descent. And then solution, the iterative approach would be, we start from some x0 or x1, and then we take, at kth iteration, we take xk, compute the gradients, add some step size, maybe small enough, and then to get k, x of k plus 1. And hopefully it converges to some point if we set alpha properly. And this, what is minimizing is that this is a conversion to squared error loss function, the minimizer of that. So this is gradient descent, but we could use like other methods too, like more advanced method, like conjugate gradient, Newton method, things like that. I mean, probably we don't want to use Newton here. Okay, is this clear? Okay. Another approach is that, okay, let's try to directly solve it, somehow like doing inverse, take the inverse of a matrix. So we can write the equation as, so we had ax equal to b, we can, okay, sorry. So this was the gradient. What was the gradient? Okay, so this was the gradient. If the gradient is equal to 0, then this would be the minimizer of it. So I just basically write that requirements of gradient being 0 in this form. So A transpose A, X is equal to A transpose B. So I solve for it. So X star, the solution would be A transpose A inverse times A transpose B. And here we assume that A transpose A is invertible matrix. So if we have a method to invert the matrix A transpose A, we can use it for solving this equation. Okay. And then we can also think of, as you mentioned, we can use iterative approach. So just one of you, I think, might be having your microphone on. I guess this is good. Yeah, I had some feedback. Okay, thanks. So we can also do it as a fixed point iterative method using some kind of fixed point iteration. So here, I just write it. I want to make it like similar to usual fixed point equations that we have seen. So we can write ax equal to b as I minus ax plus b is equal to x. So I just add x to both sides and rearrange. And suppose n is equal to t. So it's a square matrix. So this is of the form of Lx equal to x, with L being an operator or a mapping of this form that takes x and returns I minus ax plus b. So we can also write it this way. And if L is a contraction mapping, which is not always the case, it depends on the property, depends on, say, A, by the one-off fixed point theorem, which we have seen several times already, the iterative procedure that looks like this converges to X star. So how does it look like? We basically take xk, apply the Bellman, not the Bellman operator here, it's just like operator L to get x k plus 1. And if you write in form of A, it would be I minus A times xk plus B. And this converges to solution of X. If it converges, it converges to solution of X star being B. So this is the condition is that if this is a contraction mapping, which is not always the case. So we can do it for all matrices. We can also have a similar procedure, which is in this form, that instead of applying LK here completely and moving towards the, replace the current value with LXK, we can only move a little bit towards it with the learning rate of alpha. So we have alpha times LXK plus keep it 1 minus alpha times of XK, we keep it as before. So xk plus 1 would become 1 minus alpha xk plus alpha times LXK. And this is more similar, this is somehow similar to those stochastic approximation iterative methods that we had before in, say, when we talked about TD methods or Q-learning, except that there's no noise here. So this is kind of like the noiseless version of stochastic approximation, which is kind of oxymoron because there's nothing stochastic here. But the reason I'm writing it this way is because later we want to get something, the noisy version of this. So it's good to have the noiseless version written this way first, and then we'll see how it looks like later. So this is one approach. Okay, so we talked about 3 approaches for solving AX equal to B. One was optimization. Okay, it takes a while, I guess. Perfect. Yeah, I don't know what happened. Yeah. So maybe my Wi-Fi dropped. Anyway, so we had, for solving it, we can do it optimization-based approach, direct approach, and fixed point iteration approach. So I'm going to talk about now going back to projected Bellman error and kind of show what would be the equivalent of them for solving that equation or that problem. So here, let's talk about direct approach. So instead of minimization-based approach, we want to find, we see it as a linear system of equations and then use a direct approach for it. So here, we assume that the function space F is a linear function space. So F would be space of functions that can be written as phi x transpose W. W is p-dimensional. We have p basis. And the goal is to find a value function that satisfies this linear system of equations. So we have x for all x's in the state space. We want it to be such that after applying the Bellman operator and then projecting back, the value would be exactly v of x. And here, the thing is that v is restricted to be within function space f, which is linear, which means that I can write v of x as some phi transpose x times w. So this is the path that I'm going to take. And okay, so we want to find this solution with the constraint that value function is linear function space. So for simplicity of notation, everything, I assume that value function, the state space is finite. So X is finite and has capital N states. Capital N can be very large, can be million, billions, or anything, but just so that I can use the usual linear algebraic notations and matrix inversion and everything. Instead of going to infinite dimensional equivalent of matrices, so I present everything with a finite state space. So every basis function phi, which we have p of them, would be an n-dimensional vector. So essentially like phi1, say, for example, would be some vector, which basically, so it's n by 1 vector, which says that at state 1, like what is the contribution of feature 1? At state ith, what would be the contribution of feature 1? And so on for all the p different features. So we put all of them in an n by p matrix, capital phi. So I put them like this. And also the value function is, also I can represent it as an n-dimensional vector. So it would be, v would be n by 1 dimensional vector, which can be written because it is represented in the basis of phi. So it can be written as capital phi times w. So capital phi is n by p, w is p by 1. So the dimension would be n by 1, as I wrote here. So that's a kind of setup. Now I just plug these things back to that equation of fixed point equation for projected Bellman error. So we want to solving this equation means that we want to find a v which has this form that satisfies, which means that we find the w, which represents the value function, such that the value function, phi w, so this would be value function, subscript w, would be such that phi times w, the value function after applying the Bellman operator and after projection, it would be equal these two things. All right, is it clear? Okay, so let's just introduce some kind of notations. So if we have value function v1 and v2, first I want to define an inner product, mu weighted inner product between them, and then define the norm, mu weighted norm. So this is, I think, as before, but so v1, v2, when they are n-dimensional, the inner product of them weighted by mu is written as v1 summation over all x's, and x goes from, say, x1 to x capital N. So v1x, v2x, weighted by mu of x. So that's would be the inner product. And if I write, I put this mu in a diagonal form. So I write a matrix, and this would be mu of x1, mu of xn, and this is 0. So it's a diagonal matrix in that form. Then I can write it in this matrix form of v1 transpose capital M v2. So essentially M captures this weighting. And if you're not sure why this is the case, I guess easy way is just to write the definition of the matrix product and notice that if M is diagonal, only the diagonal term, or only the same indices of v1 and v2 would be chosen. I guess it's best to write it down yourself. Okay, so L2 norm of it, weighted L2 norm, would be written as V, so this is L2 norm squared, would be inner product of V by itself, which would be then the summation over all x's of Vx squared, weighted by mu x, which would be in the matrix notation V transpose MV. So this would be the norm of V, some function V. So here, yeah, so this is general. This is V is not necessarily belonging to any linear function space. So it's any vector, n-dimensional vector. Okay, then let's, what I want to do, essentially write this completely in matrix form. So one thing that I need to do is that write this projection operator in a matrix form. And I promised when we have a linear function space, we can have a kind of like a closed form solution for it. So I just want to show what it is. This is kind of standard result, but still. So we have a projection operator, capital pi of V onto a linear function space F can be written in this form. So for any V, so this is any vector, n-dimensional vector, projection of it by definition, as optimization definition, means that the closest point into that space according to norm, L2 norm weighted by mu. So here I have it V prime belonging to F, so V prime closest to V. So I just write V prime in the form of V prime is a function that can be written as some phi times W for some W. So what is changing is in optimization is actually W. Phi is the fixed one. So I write it as argmin of W in Rp of phi W minus V. Again, the L2 norm of it. I just expand it from equation that I had for L2 norm before. So it would be minimization of phi W minus V transpose times M times phi W minus V. So yeah, okay, so that's the point. Maybe I guess one thing I can mention, if V belongs to that function space, suppose V is actually can be written as W0, suppose V is in that form, then if I plug this here, so I get phi times W0, and the minimization can be done easily if I choose W to be W0, because then each of these terms would become 0, and it would be the minimizer of this argmin. But if it is W, if V is not of this phi W0 form, so it's not belonging in that function space, then the minimizer is not necessarily have as value of 0. Okay, so we have this form. We take the derivative and set it to 0, similar to what we had a few slides ago for optimization of like norm of AX minus B. So we set it equal to 0. Maybe I just go through this fast. So we have phi transpose M times phi W minus V equal to 0. I can rearrange it and solve it to get W would be phi transpose M phi, the whole thing inverse, times phi transpose times M times V. So this looks complicated, but this is just a simple algebra. So this is basically shows that what is the W is. So this is the best W we find. To find the function, we have to multiply a phi to the left side of W. So the function is of the form of, the projected function would be form of W, which means that this projection of V, which is a function, can be written as phi transpose M phi inverse, phi transpose MV. So that's the form. It looks a bit complicated, but we got it. So we had one part of that projection part. Now just let's talk about this other, the Bellman operator part. So I just want to write the Bellman operator applied to a value function phi W in some matrix form. So T pi phi W, which is n by 1 dimensional vector, would be a reward function, which is n-dimensional vector, plus gamma times p, which is n by n matrix, times phi, which is n by p, times w. So if I plug all these things together and solve the fixed point of the projected Bellman operator can be written as the solution of this linear system of equation, which on one side we have value function, which is phi w, and the other side is the projection of the Bellman operator applied to value function. Okay, so I think, is this clear so far? Okay, so maybe it's good to have a few minutes of break. Now it's like 7 minutes after. Let's start maybe 2:13. Okay, so let's continue. So we got to this point that we could write the fixed point equation for the projected Bellman operator in the matrix form. So we can either solve it directly or use through a fixed point iteration. So let's try to solve it directly, like as a matrix, get to a point that we do a matrix inversion. So this is some algebraic manipulation. So we start from this 23, we multiply both sides of it by phi transpose m and simplify. So we get like phi transpose m, phi w is phi transpose m, phi, then phi transpose m, phi inverse, phi transpose m, and then this would be the Bellman operator applied to value function represented by w. Then these two terms cancel, so we get phi transpose m times this Bellman operator, which after kind of rearranging, we get that phi transpose m times r plus gamma p phi m, phi w minus phi w is equal to 0. So if you notice, this is kind of looks like a Bellman residual term. So this is saying that how much t of v is different from v. So this is the Bellman residual. So we can rearrange this again to have w's on one side and reward on the other side, because we want to find the w. So we get to this equation, and then we take the inverse of this in order to get to the solution that w would become phi transpose m, phi minus gamma p pi phi, the whole thing inverse, times phi transpose m rp. So this solution, this is the population version of the method called least square temporal difference method, or LSTD. And this is basically saying that if we have all these matrices, if we have, say, phi, which we have, if we have p and we have the reward function, then we can find the best w in a sense that it would be the fixed point of the projected Bellman operator with just this solving this equation. This method, maybe I should say that this is LSTD refers to the case that we have data, like we estimate something like this only based on data instead of having this matrix P and everything. So it's a kind of the data-based version of it, but I use LSTD for this population-based version of it. And we will see that how we can convert this to a method that we can use data points or samples in order to estimate this W. What else I want to say here? Okay, I guess the other comment is that LSTD is known as being a data efficient method. I mean, not in this case, because this is not about data, but when we have data, it would we consider a very sample efficient method, but it is not necessarily computationally cheap because we need to do some kind of matrix inversion. We also have a Q version of this. Like instead of value function, we can try to estimate the Q. And the idea is basically very similar. We just need to write phi of Q of X and A as phi of X and A times some W. So we can do that. I mean, the formulation would be almost the same, with some small differences to incorporate the fact that we have actions too. Okay, so one other comment maybe noticing that LSTD from this equation 24. So we have phi transpose M times something that looks like Bellman residual. So we have phi transpose M times this term. Notice that, okay, so this is what LSTD minimizes or make it equal to 0. Also notice that the inner product between V1 and V2 can be written as V1 transpose M V2. So you see that we have M in both cases. Here V1 is like phi, and V2 is like this Bellman residual term. So this basically says that if we only focus on one of the features, like this would be capital phi would be p different features. We can, if it is 0 for all features, it would be 0 for each of those features too. So this entails that we have phi I, inner product of phi I and this term, t pi v minus v. And here I wrote it as v instead of phi w to be a bit more clear, which, as I said, it's a Bellman residual. So it means that inner product of phi times Bellman residual for the w should be equal to 0. So it finds this solution. So the kind of the geometric interpretation of it is that LSTD finds a w such that the Bellman residual is orthogonal to the basis of f. Because when, if v1 and v2, the inner product of them is 0, it means that they're orthogonal in that, according to this mu, of course. Okay, any question for so far? Okay, so let's talk about some fixed point based approach. We designed 2 iterative approaches for finding a fixed point of projected Bellman operator. And the goal is to design methods that look like some stochastic approximation methods. So of course, there is nothing stochastic here, but later when we have samples, having these methods make it natural to have the stochastic approximation based approaches. Okay, here, okay, we attempt to have fixed point iteration approaches. Here I'll focus the case of distribution mu is the stationary distribution rho pi of pi. So the methods are designed for that, and the reason you see that for convergence of those methods, we actually require mu to be the same as station distribution, because station distribution has these nice properties. So the first approach is like this, that we consider an iterative approach that takes v hat of k, computes, okay, and to compute the v hat of k plus 1, it takes 1 minus alpha of v hat of k plus alpha times projected Bellman operator applied to vk. And alpha is a kind of number between 0 and 1. So this is, you see, it is kind of moving towards the projected Bellman operator, but not completely. If alpha is equal to 1, it just jumps to the projected Bellman operator of vk. If alpha is smaller, close to 0, it just moves a little bit towards it. So this can be seen as the fixed point iteration method with the operator L, which L is essentially 1 minus alpha I times pi t pi, capital pi t pi of v, So this is the operator, and this can be shown to be a contraction operator. So how the basic idea is that, okay, I just write this L here, check the condition for contraction, but here I notice that I'm measuring contraction with respect to not supremum norm, which we used to do before, but with respect to the L2 norm. So it would be 1 minus alpha V1 V2 plus alpha times the difference between projection of Bellman operator being applied to V1 minus V2. So that's the operator. So I guess this first part is kind of clear, because if alpha is smaller than 1, then this is fine. But the second part, I need to show that this vector is not growing. So I need to show that it has some kind of contraction property. So one thing is that I mentioned already, the projection operator is non-expansive with respect to L2 norm. L2 norm of rho pi. And then the Bellman operator is gamma contraction with respect to the same norm. That's a kind of lemma I showed at the beginning of the lecture today. So using these two facts, I can get that this projection of T pi of V1 minus V2 is smaller or equal to T pi V1 minus V2. So this is non-expansiveness of the projection times, and then this from here to there, I use the contraction, gamma contraction of the Bellman operator with respect to rho pi to get this equation. So if I combine these two together, I get that LV1 minus LV2 would be 1 minus alpha plus alpha gamma of V1 minus V2. So as long as this is smaller than 1, then we are, L would be a contraction. And if alpha is between 0 and 1, that would be the case. And yeah, so I guess then that shows that this would be a contraction operator. So because of Banach fixed point theorem again, this would converge to its fixed points. And its fixed point would be the same as the fixed point of the original projected Bellman operator. So this would be our procedure. One comment I think that is important is this is with respect to projection operators with respect to rho pi. If we used, and also for the one, yeah, okay, so the projection with respect to rho pi. If we use some other norm for the projection, mu, we wouldn't have that non-expansiveness property necessarily. And maybe one other question from you, like analyzing this thing, like L, I wanted to show that it's contraction. Here I'm using the contraction with respect to L2 norm rho pi. So why didn't I show the same thing with respect to the supremum norm? Because we know that the Bellman operator is contraction with respect to supremum norm. Why didn't I use that? Okay. Okay, that's a time for you to think. Okay, there is one answer. So there is an alpha missing in the second term. Which slide are you talking here?
Yeah, here between 26 and 27, definition of L.
Yes, that's a good point. Yes. So there is an alpha missing there. But here, when I brought it down here, I kept it. But just in this part, there was alpha missing. Thank you. Okay, any idea why we might be?
we had a lemma earlier that said it's a contraction with respect to the stationary distribution.
Right, so that's what we used. But could we also show it with respect to supremum norm? Because at least we know that the T is contraction with respect to supremum norm. So what would be the reason that we didn't do it? I mean, we could do it possibly, and maybe it works. But maybe you can think about it. That's, oh. Okay, let's try to finish this before everything collapses. Okay, so this would be a fixed point iteration. Think about why we didn't use supremum norm. It is related to these points, that projection may have problem with contraction with respect to supremum norm. There is a comment in chat. Yes, exactly. So projection is a contraction with respect to supremum norm. It is contraction with respect to the L2 norm because it's defined based on L2 norm, with especially L2 norm with respect to that station distribution. So if, for example, we used, so what would happen if that, say, for this case, if I use another distribution, I could define projection with respect to mu. That would be contraction with respect to mu, but then T pi would not be contraction. Sorry, this part, the projection part would be non-expansive with respect to mu, but T pi would not be contraction with respect to mu. It is only contraction with respect to rho of pi. So I have to choose, because of T pi, I have to choose mu to be equal to rho pi in order to make a contraction. The same, if we had supremum norm, T pi for, say, supranorm, T pi is a contraction with respect to supremum norm, but the projection is not, because projection is minimizing things in L2 distance, in average in some sense, like L2 weighted average. But supremum norm requires that the maximum distance would become minimized, which is not the case here. Okay, so that's the kind of issue, and that is actually important because the result of these things would be that, say later when we design an RL algorithm, you see that this algorithm or something like this would be basis of TD method with function approximation or for linear function approximation. We will see that if the data distribution is not coming from the station distribution, those methods or the underlying operator defining those methods may not be contraction, which means that if they're not contraction, it may diverge. So that's why if, as opposed to case of finite state that everything was nice, in the case of linear function approximation or function approximation in general, methods like something that looks like TD would not necessarily be convergent if the data distribution is different from the behavior, the distribution of that T pi that we are evaluating. We get to that later. Okay, so this approach first, so let's just use a linear function approximation and see what happens there. So same formula, just use linear function approximation. And then I use, we have an explicit formula for the projection. Here I'm using rho pi and station distribution of pi. And instead of m in the previous formulation that I have, I use d to kind of emphasize that this is for rho pi. So m was kind of for mu, any mu, but d is for the diagonal term of station distribution. Okay, the iteration can be written as v hat k plus 1 is phi vk plus 1 minus alpha phi wk plus alpha times this projection part. And then this is the Bellman operator part. So has some formulation. I multiply both sides by phi transpose w to get phi transpose d phi wk. Same term here for WK, and I have alpha times phi transpose d phi, the inverse of it, and these terms. So assuming that phi transpose d phi is invertible, I can take the inverse of both sides, like this side and that side, in order to get kind of the dynamics of WK, so how I should update Ws. So WK plus 1 can be written as 1 minus alpha WK plus alpha times phi transpose d phi inverse phi transpose d times the Bellman operator applied to phi k, to phi WK. So this is a convergent iteration and converges to the fixed point of the Bellman, projected Bellman operator. So this would be the same solution as LSTD, but LSTD tried to find it directly by solving matrix inverse. This is an iterative approach. Is it clear? Okay, so so we get this iteration like this. One issue here is that we have this phi transpose d phi inverse. So this is a P by P matrix. So we need to do P by P matrix inversion, which is, if you do it naively, it would be order of P to the power of 3. If you do it a bit smarter, okay, that's, okay, so this was a order of P cube operation for inversion. If we do it just naively, there are better algorithms. I guess we can, Strassen algorithm is like 2.8 and almost. And then there are 2.35, 36 operation, but those are apparently not practical algorithms. So this is, anyway, the point is that this is computationally expensive. Also, we have a matrix vector multiplication at each step. So when we move to the online setting, we don't have this matrix, but we estimate it by each data, as each data point arrives. So the result would be, like, we need to do inversion every time step, which would be very time consuming. There are methods to do it kind of cheaper, but still that would be an issue. So there is another approach that tries to be more efficient. So there wouldn't be any matrix inversion or matrix vector product. So there would be everything would be computed based on just vectors. And it starts from that equation 24 that we had. I'm writing it here. Okay, so we have this equation that we got through the computation of LSTD. So phi transpose D times this Bellman residual is equal to 0. So I'm going through a few steps of argument to show how we can convert it to some iterative approach. So if we know that some operator LW is equal to 0, then multiplying by alpha LW would also be 0. So adding identity to both sides does not change the equation. So we have, I add W left side and right hand side. So W plus alpha LW is equal to W. And then, so this is form of fixed point operation equation for this operator L prime, which L prime would be a mapping from W to I plus alpha LW. So the fixed point of it would be the same as the original one. So now I can apply L prime iteratively in order to get to W star, the solution of it. So I apply WK plus 1 being equal to L prime WK equal to I plus alpha L WK, assuming that is, of course, contraction. So to relate it to what we had here, so from this equation 28, I define a kind of this L to be equal to that value. So L is a mapping from W from phi transpose D pi, this Bellman residual part, and we follow the similar iterative procedure to get this equation. That would be WK plus 1 is WK plus alpha times D pi, R pi plus gamma P pi phi wk minus phi k. So this that I highlighted would be the Bellman residual, but it's weighted according to this dpi. And I just add w to it. And also it can be written in this form with some specific form of w. So this is not exactly like a convex combination of projected Bellman operator and identity matrix. In the previous case, it was the case. And we showed that if it was like we had this convex combination of them, we still maintain the contraction property. We use a kind of simple argument that we had there. Here we can't use that because it's not a convex combination of projection of Bellman operator. But still we can show that this is convergent if we choose alpha small enough. Previously alpha had to be, could be any number between 0 and 1, but this is, alpha should be small enough. And here we don't have matrix multiplication anymore. I mean, there is dpi, which is a matrix, but it's a diagonal matrix. So everything, it is essentially as well behaving as a vector. So we can do all this computation with just vector computation. I mean, the only thing is that we have p pi phi, but we will later see that, I mean, this is kind of unavoidable. And we will later see that we can replace this with sample. So the sample-based version of it would be a method that does only vector-based computation. And if the vectors are p-dimensional, so the order of computation per step would be order of p. And the kind of interesting thing is that this method would be, when we compare it, convert to the sample-based version, it would be essentially TD method for linear function approximation. So this is how we get the TD method. Okay, so there is an error bound on the LSTD solution. Suppose, I think some of you ask, like, what can we say about which Bellman residual minimization or LSTD solution, which one is better? I mean, we have upper bounds for both of them. We can talk about upper bounds. Upper bounds are not necessarily revealing everything about how well a method works, but they reveal something. At the minimum, they show that if we can find an upper bound, that the method is sound, it is working. So here the idea is that suppose we find a V that satisfies this equation. We know that for linear function approximation, LSTD solves it. And also the fixed point iteration, two different approaches that we talked about, also finds that solution. So we call that solution TD method, or TD solution, and sometimes we denote it V of TD. We could also call it V of LSTD or LSTD solution. So all of them converge to the same point, either directly or iteratively. Now the question is that how close is this value function, VTD, to V pi? So is it any good or not? So there are some comments, is that if the value function space cannot represent V pi, so V pi is outside that space, we are this space, so there is distance, then, and which is the case often the case in function approximation, we cannot expect to have zero error. Maybe small error is not very accurate here. It should be zero error. And depending on how far this V pi from this space of value functions, the error can be small or large, like small or large. The smallest error that we can hope is the projection of, okay, there is an issue here. So it should be the norm of projection of V pi to F and minus V pi. So capital pi, V pi minus V pi, that's the smallest error we can hope, which is because that's the projection is the smallest, is the point in that function space that has the smallest distance to that V pi. So that's the smallest we can hope for. TD solution does not find that point. It finds some other point, but that point is not going to be far away from the best points. How far away? This result basically shows that if rho pi is a station distribution. So if we measure distances according to station distribution, then the difference between VTD and V pi, according to L2 distance weighted with rho pi, is going to be upper bounded by, so there is again something missing here. It would be the projection of V pi minus V pi. The whole thing divided by square root of 1 minus gamma squared. So this 1 divided by 1 minus square root of 1 minus gamma squared is going to be larger than 1 if gamma is larger than 0. So this shows that the left-hand side is going to be larger than the minimum distance that we can find. And how large it is depends on gamma. Is this clear? So this is a kind of error bound that we have for the quality of the TD solution. Okay, so this is kind of, I guess, most of what I wanted to talk about population-based methods. So these are idealized methods when we have data. We don't have data. Now the next step, I want to talk about data. So here the idea is that we have data, we don't have the model, how we can compute the same quantities like value function, Q pi, V pi, or things like that, or eventually Q star and then pi star. So the key idea is that finding empirical version of the relevant quantities and estimate them using data. So for example, many of the methods that we had required the computation of TV. So I use T in order to either refer to T pi of V or T star of V. So if the model is not known, this cannot be computed. And we have to come up with some procedure to estimate T pi only based on data. So we can talk about two kind of classes of setting, data setting. One is batch setting, batch data setting, and the other online setting. Online setting, you saw it in the previous lecture, like the learning from a stream of data, that we had those kind of online algorithms that as each new data point arrives, you update, say, for example, the value function. TD method is an example of it. Here, the setting is a batch setting, which is the data is already collected, and we are interested, so it's collected. The agent is not interacting with the environment anymore. And now we are interested in using it to estimate quantities like Q pi or Q star. So what is the form of the data? The form of data is like these n tuples of xi, ai, ri, and xi prime. So xi and ai assume that coming from some distribution mu. And then xi prime is a next state condition on xi ai, and the reward is also the corresponding reward. So it's kind of like we're at one point, we move one step, and that's our tuple. Sometimes we might have a policy that is generating data like following a trajectory, and in that case, we have a stream of data like x1, a1, r1, x2, r2, r2, and so on and so forth. And in that case, x prime of t would becomes x of t plus 1. So there is this consequence between them. But we don't have that assumption necessary. Sometimes xi AIs are randomly generated, maybe IID generated, and then we only have one next step. So this is the batch setting. So as I mentioned, the batch setting, the agent is not interacting with the environment. This can be contrasted with the online methods such as TD and Q-learning, where the agent updates the estimate as it's interacting. Also, I should mention that the boundary between batch method and online methods kind of blurry a little bit. So it's not like that a method is either completely batch or completely online, because some methods may collect a bunch of data points, like 100 data points, 1,000 data points, or even 5 data points, do some processing on them, compute a new, say, value function or a policy, and then use this new policy to collect data. And then they continue. So depending on like how much we do processing, it can be one point in the spectrum of completely purely online versus purely batch. So maybe one thing, maybe I guess 2 reasons I can remember right now that why we talk about batch methods. One reason is practical reason is that in some problems, we have a lot of data that has been collected before without an RL algorithm being in the loop. So you have a chemical plant, you have a controller, it has collected a lot of data, but that agent that controlled it wasn't a reinforcement learning agent. And now you want to have a reinforcement learning agent that gets that data and find a policy that is better than the previous case. And in some setting, we don't really want the RL agent to directly interact with the environment, at least in the beginning of learning, because if it doesn't know anything, that might be dangerous for, say, a chemical plant or autonomous car or something like that. So that's why we collect a batch of data using a policy that is kind of safe. And then after the method learns a lot of, collect a lot of data and process it, find a good value function or good policy, then we let it interact with the environment. So that's one practical perspective. The other is theoretical perspective. Is the theoretical perspective, in some cases at least, analysis of batch RL algorithm might be easier in some cases. So we use it as maybe the first approximation of trying to understand the method and providing some results like sample complexity results, saying that if you have n number of data points, how well we are going to behave. So that's from theoretical perspective. Okay, so
can I ask one question?
Oh, yes.
Yeah, so is the batch reinforcement learning the superset of offline and off policy? It seems that both cases can be batch.
Okay, so that's a good, offline is like batch here. I use it equivalently. Off policy, and in many cases it becomes off policy because the policy that collects data, pi b, might be different from the policy that we want to evaluate. But sometimes maybe we just want to evaluate pi b, and in that case it would be online. Yeah, so I think people also use offline methods to refer to batch methods. So one thing is that, okay, I will go a little bit of, well, more than a little bit over time, but I kind of want to finish this lecture so that you can do homework assignments. So I try to skip some of the less important slides, but feel free to leave. So I just keep going to record the lecture. So, okay, so we have a batch of, let's try to devise some methods. One is that we want to approximate the value function given the Monte Carlo estimates. So here the batch of data is a bit different from what I had in the previous slide. So we have a batch of data in the form of xi, ai, and return of policy pi when we start from xi, ai. So g pi of xi, ai means that we have a return of being at state xi, take action ai, and then after that, we follow policy pi. And the distribution would be like this. So we can, and you remember, we could compute how the Monte Carlo worked and what properties it had. Like, for example, if we had initial state only version of Monte Carlo, it provides an unbiased estimate of the return. Right? Okay, so we essentially have a batch of data points that we select XIAI, follow the policy afterwards, so until end of episode, for example, and this gives us an unbiased estimate, but noisy estimate of the value function at that point. So in previous lecture, I talked about population version of this value function approximation when we had q pi, and we want to find minimize q in the function space that minimize this L2 norm. Here we don't have q pi, and we don't have mu. We don't have direct, okay, so we don't know q pi, but instead we only have unbiased estimate g pi of q pi at a finite number of data points. So that's one difference, which is also, I guess, implying that we don't have the distribution mu, but we only have some samples from that distribution mu. So recall that here, the assumption is that the distribution of xiai's comes from mu. So we want to convert this to a method that we can, this minimization, similar minimization problem or optimization problem that we can solve. So the first claim is that having access to unbiased noisy estimate of q pi does not change the solution of the minimization problem. So this is, you might have seen something like this in your introduction to machine learning algorithm. Of course, not with q, but so here for any q, we can decompose the expectation of squared value of q of xi, x and a, and g pi to, by, in this form, but we add and subtract q pi of x and a, q pi and x and a. So, and then we take this to the power of 2. So we will have a term like q minus q pi squared plus expectation of q pi minus g pi squared plus another term, which is like inner product of them, which would be like 2 times expectation of the first term and second term. So q minus q pi times q pi minus g pi. Okay? So this is just taking this to the power of 2. And the first term, this term, is essentially L2 norm of q minus q pi squared. So there should be a squared here too, according to distribution of mu. So this expectation and L2 norm is by definition is the same. And the second term is essentially this is saying that the difference between q pi and g pi. G pi is a random version of q pi because it is unbiased, so its mean is the same as q pi. So it is around q pi, fluctuating around q pi. So this would be essentially a variance of g pi. So we can write it as expectation of conditional variance of g pi of xa. And condition is here by x and a. So this is second term. The inner product term is going to be 0, this last term. And the reason is that, so we can expand this. This looks complicated, but it is just because there are a lot of notations, but it's not complicated. So we have this expectation. I convert it to expectation. The inner expectation would be conditional on xa. So inner expectation is conditional on xa, taking expectation with respect to the randomness other than x and a, which means that the randomness in trajectory after we start from x and a. So randomness of following pi. And the outside expectation is with respect to the randomness in x and a. So I convert this in 2 parts. And then we have this, so look at this inside. The first term, let's see which part is random and which part is not random. Condition x and a. So q of xa minus q pi xa, that is not random when it's conditioned on x and a, because q is a given function, and x and a is because we are conditioning it, so it's not random. Q pi is a fixed function, it's a value function, so it's not random. So these things come, there's this property of conditional expectation that if it is something is not random, it can come out of that conditional expectation. So we have that this term becomes coming out of the expectation. For the second term, we can also do the same argument. Q pi is not random, conditional x and a, but G pi is random, conditional x and a. But we can write it, so we write it as expectation of G pi x and a, condition x and a. So there is this randomness that is because of following a trajectory after x and a. But the thing is that the conditional expectation of this term, conditional expectation of return, is exactly the same as Q pi. That's a definition of Q pi. Q pi is the expectation, conditional value function's conditional expectation of the return. G pi is return, so when I'm computing the expectation of it, so this term would become exactly equal to Q pi. So this whole term, this parenthesis, becomes 0. So the whole thing becomes 0. So we had 3 terms. We converted to 3. The last one was, the inner product one was 0, and we had another form for the first and second term. So now suppose we do the minimization of our Q functions in F of Q minus G pi. So this is what we can kind of compute. There is one step. But if we have returns instead of Q pi, this is what we get. And then by expansion that I showed, this is equivalent of expectation of Q minus Q pi squared plus expectation of variance of G pi. And the last term was 0, so we don't have it. So interesting thing here is that this second term here is not a function of Q. It is just a variance of G pi. So it doesn't matter what Q you choose. This does not change your minimizer. It changes the value of the minimization problem, but it doesn't change it's like a constant, but it doesn't change the location of the minimizer. So the minimizer would be essentially only the first term, which was Q minus Q pi squared. So this shows that what we can kind of compute from data, if we have only returns but not Q pi, the minimizer would be the same as the case that we have Q pi, which is kind of like the population version of the loss. So this is great. But we can't compute the expectation because we do not know mu. We don't have mu. So here there's mu. We don't have mu, but we only have samples. So a common solution to this problem is that when we have samples from a distribution, we can't minimize the population loss, so let's minimize the empirical loss. So this is also called empirical risk minimization, which means that let's try to find a Q hat, which minimizes Q in that function space again. But we have a loss function that is summation over 1 over n of 1 to n of Q of xiai minus G pi of xiai squared. So you see that we have everything here. We have xiai's. By assumption, we had these returns. So we can form this loss function and then try to minimize this. So sometimes I use this other notation, which instead of having summation, I write L2 norm of dn here. So there's dn here, which basically shows that this is only data dependent. Sometimes I also use it only n instead of n. But so this is more compact notation. And if you pay attention, this is essentially a regression problem with squared error loss. So the targets are the returns G pi's, and we want to find the Q that fits to that target well while avoiding overfitting and things like that. So this means that if you have Monte Carlo estimates, we can solve a regression problem, and any regression method that you have, any function approximator, can be linear function approximator, neural network, decision tree, or whatever, you can use it to solve this problem. So people also you can add regularizer in order to control for the overfitting. So there are some questions. One is that, okay, how close is this Q hat to the minimizer of population loss. The other question is that this Q hat, how is it going to be a good approximation of Q pi or not? And another is that what's the effect of number of data points? Like what's the difference if instead of 10 data points, we have 1,000,000 data points? What is the effect of it? And the other is that what's the effect of the function space F? What happens if you use a neural network with certain architecture? Okay, so I think I skipped this. So in lecture notes, you see there is these results. In a very simplified setting, try to analyze this regression problem. If you have taken any course on statistical learning theory, you have already seen this. If not, probably you haven't, but unless your research is on that. So in very simple case, I try to analyze it. Let me skip it. Maybe next lecture I talk about it if I have time. So I want to talk about this other algorithm, which is called approximate value iteration. But maybe before that, is there any questions so far? Okay, so you remember we had this approximate value iteration. We discussed in a population case that we find qk plus 1 or vk plus 1 as the minimizer of this L2 norm, which was minimizer over q of q minus t qk. And this was either t pi or t star. Previously, I guess I showed it for value function, state value function v, but we can do it with q2. And this is a norm. This norm is essentially this integral or expectation of q of xa minus t of tq of xa squared rated by mu of xa. So again, like previous case, we cannot compute this because of two reasons. One is that mu is not known. We don't have mu in the case of batch RL. We only have samples from it. The other is that tqk cannot be computed because we do not know dynamics p. We don't have dynamics p, but we only have data from it in the form of next states coming from that distribution. So this is essentially going a somehow similar path, try to find the empirical version of this population loss function. So if you are only given data points in the form of tuples x, a, or x prime, and x prime being next state, we cannot compute this Bellman equation, or similar for T star, but we can compute the empirical Bellman operator applied to Q. And that would be an unbiased estimate of it. Recall from a few lectures ago that T hat of pi, or T pi hat, or T star hat, are the empirical Bellman operator or empirical Bellman optimality operator defined as, okay, so there should be this x and a, so we have r, there's no I here, plus gamma times q of x prime, p of x prime, pi of x prime, sorry. And for the Bellman optimality, empirical Bellman optimality operator, it would be max here. And as we showed before, and I guess you can see it by taking just conditional expectation, the conditional expectation of the t hat q of x and a, condition x and a, would be essentially the same as tq x and a. So this is kind of similar to the previous case that if you remember, the return is unbiased estimate of value function. Here, this is the empirical Bellman operator applied to Q. That's not unbiased estimate of value function, but it is unbiased estimate of TQ, Bellman operator being applied to Q. And that's all we need. The rest would be this kind of the same as before. So I want to show that replacing TQK with T hat QK does not change the optimizer. So the argument is again the same as before. I only go through it quickly. So expectation of QZ minus T hat QKZ, and Z the shorthand notation for X and A. So I use it to make it more compact. So I just add and subtract TQK of Z, do the same decomposition as before, So we get 3 terms. The last term is 0 exactly for the same reason, because we take the expectation and move the conditional expectation inside. We would have conditional expectation of t hat qk of z, which would be essentially this form. That would be exactly equal to tq, and which makes this whole parenthesis equal to 0. So this third term, the inner product term, would become 0. And also we argue that condition on z, the function q minus t qkz is not random. So we can take it out of the expectation. So we get this form. Maybe I skip a little bit. So now I take the expectation with respect to z of the difference between q of z minus the empirical Bellman operator applied to qk. And then I use what I had in the previous slides to decompose it to 2 terms. One is that expectation of expectation of squared value of qz minus t qk of z. And then another one would be the expectation of variance of this empirical Bellman operator applied to z. The first term is the norm, the difference between q and t qk. So I should remove z's here. So the norm gets rid of it. So what I get is that eventually we will have a method like, if we minimize this expectation that has empirical Bellman operator here, the solution would be the same as the minimization, again z should be removed here, of q minus t qk. And this was exactly the population version of the approximate value iteration. So replacing tqk with t hat qk does not change the minimizer. So that's the kind of important thing. Again, we don't have mu, so we replace samples with it. We use samples to replace it, and we get that q hat would be minimizer of this summation of q of xiai minus t hat qk of xiai, which can be written in this more compact form too. So this is called approximate value iteration procedure, also known as fitted value iteration or fitted q iteration. It's called fitted because we are essentially fitting a q function to something, and that something is the effect of empirical Bellman operator on qk's. So this is fitted value or fitted q iteration. One thing I guess that is important to notice that we are minimizing over q. This is not being minimized. So this is qk, this is the value function that we get from the previous iteration. We only find the new value function that fits to this value. So this is again a regression problem with the squared error loss. And one, I guess, important comment is that this is the basis of Dpq Network Algorithm, which is essentially solving this iteratively. So DQN is a fitted Q iteration algorithm where we are using a deep neural network, like in the original work, use deep convolutional neural network to represent Q. So this function space F is going to be the represented by Dpq deep neural network. There are, of course, some tricks that they use for making it work with neural network, and also there are some approximation for it. For example, one approximation they use is that we can't really find a minimizer in the space of all in space of all weights of that neural network. So that's why we only do it for several thousand steps of stochastic gradient descent type of update to minimize this, instead of finding the global minimum. So the way I presented it is like the idealized, kind of idealized version that we find the global minimum. If we cannot find the global minimum, we just move towards it to some extent. Then if you read the paper, and I guess that would be one of the papers that you may read in the reading assignments, would be that in DQN, we talk about target network. Target network would essentially be QK. And the current value network would be Q. So we have a value network Q, we have a target network QK. In DQN, after certain updates, like 10,000 steps of 10,000 updates, we copy the target network to the current network and copy the current value network to the target network, and now we keep moving with the new value network, which essentially mean that we are getting here, we are computing QK plus 1 based on QK, and we are just doing it iteratively. I guess, and they also have like experience replay buffer, which is essentially storing all the data points collected so that we can compute this summation or approximate that summation. One other comment I want to mention in general for this fitted Q iteration algorithm, we have regularized versions of it, which we will, instead of solving empirical risk minimization, we have a regularized version of it. So we have a regularization term here, and that's called regularized fitted Q iteration. And that's helpful when the function space is large and you might want to avoid overfitting. I think that's all. Yes, okay, so we haven't finished this, but value function approximation is a large topic in RL. So I think next, I'm going to talk about it for online methods next. Like I'm going to talk about LSTD next time, and also online method, which would be TD with function approximation. And then maybe we start with the policy gradient method. I think that's all. Is there any question?